So the theory of small strain elastoplasticity that we are going to learn is known as the phenomenological theory of plasticity. What that means is the following. Uh, Many of you would have done a uniaxial stress strain test. So you take a dog bone specimen and put it in a UTM and pull it with forces, and you obtain a stress strain curve. Most of you would have done it for steel. So the stress strain curve looks like the straight part, then something like this. If you do it for aluminium, you would get something like this. So um, what a phenomenological theory tries to do is tries to explain the phenomenon that you are seeing through a mathematical model. It does not go into the material scientific aspects of why plasticity happens or how it progresses. It tries to describe plasticity based on what we see in these kinds of uniaxial tests. So we are going to do a very simple theory at the beginning where we are going to assume that there's an elastic part, linear, and then the material is perfectly plastic. This behavior is called an hardening behavior, and we are going to neglect it for the time being, and we are going to use a perfectly plastic model of a uniaxial tension experiment where, if you remember, the state of stress in this region is purely uniaxial. So the state of stress is purely in the direction of the stretch, and all other stresses are equal to 0. That is why the sample is made in this dog bone shape uh, in order to obtain a almost perfectly uniaxial situation at the middle of the specimen called the gauge length. So we are going to assume at the beginning that the material behaves in a perfectly plastic manner, and we have a perfectly uniaxial situation prevailing at a point in the material. So if I now perform a uniaxial test, what do I see? I start loading the material. It first goes linearly, and then since it's perfectly plastic at a stress sigma y, the stress stays constant at that value. That is, sigma y is the maximum stress that the material can bear uniaxially. It cannot take a stress which is more than sigma y. Now let us define a function which is sigma minus sigma y, and uh, I plot this function. So this axis, plot this function against sigma. So this axis is my phi equal to 0 axis, and phi sigma goes this way. Now if I load the material from this state, then here uh, phi is equal to sigma y. Phi is equal to sigma y at this point. Now when I load it and unload it, it goes all the way from phi equal to sigma y minus sigma y, sorry, phi equal to minus sigma y to 0 and comes back. So it goes to 0 and comes back, and it will never cross 0 because it remains constant thereafter. So this is a function that will go to 0 even when I load in the plastic regime. It will first increase from minus sigma y to 0 and then remain at 0. So phi sigma never crosses the 0 line. This is the first property of this function, which explains the phenomenology of whatever we have seen so far. Now if I unload the specimen, so I start from here, that is phi goes from minus sigma y, it goes up to 0, then it remains at 0, and then I come back again, then this is what it happens. It gets stuck at 0, remains stuck at 0, and then it comes back again to minus sigma y. This is what it going to do even when I am unloading the specimen. Note that the phenomenology also suggests that this slope during loading and the slope during unloading is parallel to each other, is the same, the slope is the same, the lines are parallel to each other, which is something that we see for metals. We see that whenever we unload from some point, it unloads elastically, and then when we reload, it loads elastically again up to this point before yielding plastically and following this curve. So this is part of the phenomenology, and that part of the phenomenology is captured by this function phi sigma, which uh, has the property that it never exceeds 0. So phi sigma is always less than equal to 0. Also, the total strain that I have applied uniaxially is this. This is the total uniaxial strain, which we call epsilon. And this is the elastic part of the strain, which we call epsilon E. And the rest is the plastic part of the strain, which remains in the material even after it is unloaded back to zero stress. So this is the permanent strain that remains inside the material. So if I look at strain versus time as I load, remain plastic and unload, this is what is going to happen. So first I'm going to load, and till I reach the elastic limit, strain increases linearly with time. Then I load along the plastic regime, strain keeps on increasing, and then I unload and the strain keeps on decreasing, and finally it doesn't decrease all the way back to 0, but a strain of epsilon p remains in the material point. So that's a plastic strain. So at this is the first condition that I have, that phi sigma is always less than 0. And also, how do I distinguish between loading and unloading? I distinguish between loading and unloading as epsilon dot is greater than 0 during the loading phase, be it elastic or be it plastic. Be I on this branch or on this branch, epsilon dot is greater than equal to 0. Only when I start unloading does epsilon dot become less than 0. So whether the sign of epsilon dot will tell me, the sign of epsilon dot will tell me that whether I am in the loading phase or in the unloading phase. In the loading phase, I can be on the elastic path or on the perfectly plastic part. How do I know that? If epsilon dot is greater than 0 and phi sigma is less than 0, then I know I'm elastic. If phi sigma is equal to 0, epsilon dot is greater than 0, I know that I am on this branch. If phi sigma is less than 0 and epsilon dot is less than 0 as well, I know I am on the unloading branch. So this phenomenology can be brought out by a function phi sigma, as well as another quantity epsilon dot, whose signs we have to monitor. So let us expand this a little bit more. This is your strain versus time. Now, uh, in the first stage, epsilon dot is equal to 0. So in this part, epsilon dot is equal to 0, but there is no plastic strain. I'm going elastically, so I'm going elastically up here. In this part, there's no plastic strain, which means that if I load and unload, I will come back to the same point and there will be no permanent strain remaining. So in this part, this condition is valid, this condition is valid, and of course this condition is valid because epsilon p is equal to 0. In the next part, okay, so and also in this part, phi sigma is less than 0 because of the way I have defined it. So this is the condition for this part of the curve. This part of the curve, these are the conditions that I should have. Then when I am in this region, epsilon dot is increasing, of course. Epsilon p is not equal to 0 and epsilon p dot is greater than 0, and phi is equal to 0. So this is the condition on this part of the curve. Then I start unloading. When I start unloading, epsilon dot is less than 0. Epsilon p dot is equal to 0 because unloading is elastic. This slope is same as this slope. So I'll have phi less than 0, epsilon dot less than 0 here, and epsilon p dot equal to 0. Epsilon p may or may not be 0, but epsilon p dot is equal to 0. So these are the conditions for the loading, elastic loading, plastic loading, and elastic unloading branches of this one-dimensional uniaxial curve. This is not enough because I can I can actually go in the negative direction also. I need not stop here. I can go further down and I can go into the negative compressive regime. So let's look at that in totality. So here is a material. I can go in the positive direction, go up to sigma y and unload, or I can go in the negative direction, uh, have plasticity and then unload back to 0. So I can go like this or this. So my theory should be able to explain this whole phenomenology. So these are the different branches. So in the negative part, we have already seen it for the positive part. For the negative part, here epsilon dot is less than 0. It's going in the negative direction. Epsilon p is equal to 0 and epsilon p dot is equal to 0. In this branch, epsilon dot is less than 0 again because I'm in the negative strain regime, I'm in the compressive regime. Epsilon p is not equal to 0 and epsilon p dot is decreasing because I have plasticity here in the compressive. And here epsilon dot is greater than 0 and epsilon p dot is equal to 0. So uh, on the other part, I have these conditions which we have explained already. And how do I put all this together? Uh, so to do that, I'll have to make a small modification to my phi function. So we will redefine phi as mod sigma minus sigma y. So if I define it like that, phi will be less than 0 in this part, phi will be equal to 0 in this part, and phi will be less than equal to 0 in this part, exactly like this part, and this part. So phi less than 0 here, phi equal to 0 here, phi less than 0 here. So this modification actually, and defining phi to be always less than or equal to 0, it actually explains the behavior of phi all over the compressive as well as in the tensile regime. Also, epsilon p dot I can define as lambda dot sine of sigma. So if I define it this way, then sine of sigma is -1 in this part. So in this part, epsilon p dot and lambda dot is always greater than 0. This is my definition. So lambda dot is a positive quantity, and this can be a positive or negative quantity depending on whether you are on the positive side, compressive side, or on the tensile side. On the tensile side, epsilon p dot is equal to 0 here. So lambda dot is 0 for this branch. Lambda dot is something for this branch, but epsilon p dot is positive because sine of sigma is positive. Same here. Here, sine of sigma is negative, so epsilon p dot here, epsilon p dot is negative, and same here because this sine of sigma is a negative quantity. So epsilon p dot has been defined in such a way that in this part it is positive, in this part it is negative. So it takes care of both the compressive plastic region as well as the tensile plastic region. Okay, so this is my final definition, which gives me the uh, growth of the plastic strain from this point to this point as well as from this point to this point. And this function also defines uh, the maximum stress that the body can attain in the compressive regime as well as in the tensile regime. So, so this is another way of illustrating it. So I have now done compressive as well as tensile regime. So this is my tensile and this is compressive. So this is my material point. Initially it is at zero stress. So it can go only up to the point where phi sigma is equal to 0 or sigma is equal to sigma y in the compressive direction, in the tensile direction. After this, it will have plasticity, but at plasticity, phi sigma will remain equal to 0, so it will remain here. Now, when you look at epsilon p dot, it is greater than 0 beyond this point. So, from here to here, you have elastic. When you are stuck here, you are still elastic, but if you start increasing the strain, then you accumulate plasticity, and the plasticity accumulation is in the positive direction. So epsilon p dot can be greater than 0, but phi sigma remains stuck at 0 at this point. Then you unload, you go to the other direction, you get stuck at phi sigma equal to 0 again, but sigma is now equal to minus sigma y, and uh, epsilon p dot will be in the negative direction. So you will now accumulate plastic strain in the negative direction, so it points in the other direction. So this is your elastic region. Your elastic boundaries of the elastic region are fixed, because you have a perfectly plastic material that always yields at the same stress. And this is known as your yield criteria. So remember, we have defined phi sigma is equal to mod sigma minus sigma y. So um, this is my yield condition, and I have a flow rule. I have a flow rule which gives me lambda p equal to lambda dot sine sigma, which can be written as lambda dot d phi d sigma. So if I take d phi d sigma here, this is a constant, so this goes to 0. At mod of sigma becomes sine of sigma when I do d phi d sigma. So this sine of sigma, we have already seen that this is a reasonable way of expressing epsilon p dot both in the compressive and tensile regimes. And then when I put sine of sigma as d phi d sigma, I have epsilon p dot equal to lambda dot d phi d sigma, where lambda dot is greater than or equal to 0. It is equal to 0 in the elastic regime, or in the unloading regime it is greater than 0 only when it is plastically deforming. Now we can put all this in a very compact form, what is known as the Kantuker conditions. The Kantuker conditions uh, tell you that you have two quantities, lambda dot greater than equal to 0 and phi less than equal to 0, in such a way that lambda dot times phi is equal to 0. This is a very compact way of expressing all that we have learned. So what have we learned? When is lambda dot equal to 0? When lambda dot is equal to 0, you have either elastic loading or elastic unloading. That's when lambda dot is equal to 0. When lambda dot is equal to 0, so lambda dot is 0, and phi can therefore take any value, and phi is always less than equal to 0. So phi will be less than 0 when lambda dot equal to 0. Remember, when you have elastic loading or elastic unloading, your phi is less than 0. So that can happen because lambda dot is at that point equal to 0. On the other hand, if lambda dot is greater than 0, then for this condition to be valid, phi has to be equal to 0, which is the case when you have plastic loading. Then phi is equal to 0. um, Phi is then stuck at 0, whether you are in the tensile regime or compressive regime. Phi is stuck at 0, and therefore these Khan-Tucker conditions uh, give you this whole story that I have tried to explain through these past 3 slides in one single very succinct condition. Okay, so